Hello everyone, and welcome back to the video lecture series for confidence intervals for statistics. In this video, we are going to be constructing confidence intervals to estimate the population variance and the population standard deviation. So, just like any other confidence interval, like for mean or for proportion, to construct a confidence interval for standard deviation and variance, you need point estimates for the population variance and for the population standard deviation. Remember, the symbol for population variance is sigma squared. So the point estimate for sigma squared is going to be s squared. So the point estimate for population variance is going to be the sample variance. Remember also that the symbol for population standard deviation is sigma, so the point estimate for sigma is s, or the point estimate for population standard deviation is the sample standard deviation. Now remember, variance is simply standard deviation squared. You can also think of this as that the standard deviation is the square root of variance. So the thing with variance and standard deviation is we are not going to be using the normal distribution and we are not going to be using the t-distribution. Instead, to construct a confidence interval for the variance and the standard deviation, you are going to use a new distribution called the chi-square distribution. And the chi-square distribution is extremely different from either the normal distribution or the t-distribution. The biggest difference is that it's not bell-shaped. The chi-square distribution actually looks a little something like this. It's got a bell-ish shape, but it doesn't have that nice symmetric bell shape. It's really skewed to the right. So a couple properties of the chi-square distribution is that all values of chi-square are actually greater than or equal to 0. So that means that all chi-square critical values are going to be positive. And the chi-square distribution is a family of curves, a lot like the t-distribution, where the shape of the chi-square distribution is defined by the parameter called the degrees of freedom. That should sound familiar. The degrees of freedom here, just like with the t-distribution, is going to be the sample size n minus 1. So to form the confidence interval, we're going to use the chi-square distribution with degrees of freedom being 1 less than the sample size. So your degrees of freedom will be the sample size n minus 1. Now the total area underneath the chi-square distribution is equal to 1. And this fourth property right here is actually extremely important. The chi-square distribution is positively skewed. It means it is skewed to the right, and if you look at this, it is obviously not at all symmetric. So because it is not symmetric, the tails are not the same. So this distribution is not symmetric. So the chi-square distribution is going to be different for each degrees of freedom. As the degrees of freedom increases, the chi-square distribution approaches the normal distribution. But it is not symmetric, and you have to remember that. So the left critical value for chi-square and the right critical value for chi-square are not going to be the same. The tails are not the same. It is not symmetric. So the left critical value and the right critical value are not going to be opposites. It's not just going to be a matter of one's positive, one's negative. They are going to be two completely different positive numbers. So your right critical value and your left critical value need to be calculated separately, and they need to be looked up separately. It's not like with the z-scores that we could just do their opposites. You can't do that here because this is not a symmetric distribution. So here's how to actually find the critical values in the chi-square table. The chi-square table has been posted on Canvas under the Modules tab, and it is also available on the Files tab under the Tables folder. And you can look up a picture of the chi-square distribution right in my Stat Lab, right in your homeworks, or the electronic textbook that is available on my Stat Lab. So when you are using the chi-square table, you do need to do a little bit of math first before you go looking things up. There are two critical values for each level of confidence C, and remember C is going to be a decimal. So the chi-square R, that's how you read this is read as chi-square R, represents the right tail critical value. Now to look to figure out what you're looking up, you do need to do a little bit of calculating. So the area to the right of chi-square r is going to be equal to 1 minus the level of confidence divided by 2. Now the left critical value is denoted by chi-square L. So chi-square L is the left critical value, and the area to the right of chi-square L is going to be 1 plus the level of confidence C divided by 2. So the chi-square table will give what is called alpha. Alpha is the area to the right of the critical value in question. So in this case, the area to the right of chi-square L will be 1 minus C over 2. So here's, chi-square R. And the area to the right is denoted as alpha. Then for the left critical value for chi-square L, sorry, that is not a good drawing. So for the area to the right of chi-square L, that right there is going to be alpha, and that will be chi-square L. So each area that is listed in the top row gives the region under the chi-square distribution to the right of the critical value, and each of the rows is going to be the degrees of freedom. So the columns are each the areas to the right, which are called alpha, and the rows are the degrees of freedom. This is a snippet of the chi-square table. You can find this on Canvas, remember. So just before we get into this, just to outline the table, remember the area to the right alpha is the area to the right of the critical value in question. So this alpha up here, each of these numbers represent the most common areas to the right. So we've got a bunch of areas to the right, and then each of these rows are the degrees of freedom. So what we're going to do is we're going to find the critical values chi-square R and chi-square L that go with a 95% confidence interval when the sample size is equal to 18. So since the sample size n is equal to 18, the chi-square distribution does depend on degrees of freedom. So the degrees of freedom is going to be 1 less than the sample size, so we get 17 degrees of freedom. Then we're going to do a little bit of calculating first, so we need to find first the area to the right of our chi-square R. So we're going to start with chi-square R. The area to the right of chi-square R is going to be the formula 1 minus C over 2. So since we have a 95% confidence interval, that means our C is equal to 0.95. So the area to the right of chi-square R is going to be 1 minus 0.95 all over 2, which will give us an area to the right of 0.025. So 0.025 is the alpha that we are looking up. I'm going to switch colors really quick. So let's look this up in the chi-square distribution table. So the alpha that we're going to, hold on, I think I just broke something. Give me a second. Okay, let's try that again. So the alpha that you are going to be looking up is 0.025, which is this column right there. So you're going to look up 0.025 with 17 degrees of freedom. So we're going to go down here to 17 degrees of freedom. And where they meet in the middle is going to be your chi-square R. So your chi-square R is going to be 30.191. So chi-square R is going to be equal to 30.191. Then we're going to do that again with a slightly different formula for chi-square L. Let me just switch colors. Hopefully I don't break it again. All right, so the area to the right of chi-square L is given by the formula 1 plus C over 2. So the area to the right of chi-square L is going to be 1 plus the level of confidence, 0.95, all over 2, which gives us an area to the right of 0.975. So that 0.975 is the alpha that you are going to look up when you look up the chi-square L in the table. Let me switch colors one more time. Hopefully this doesn't break it again. So we're going to be looking up an alpha of 0.975 this time. So we're going to go into this column with still 17 degrees of freedom. So we're still going to go down to this row, and where they meet in the middle is right there. So we get a chi-square L value of 7.564. So in the chi-square distribution with 17 degrees of freedom, the two critical values that go with a 95% level of confidence are going to be a chi-square R of 30.191 and a chi-square L of 7.564. So you're going to use those critical values to calculate the confidence intervals for sigma squared, population variance, and sigma, population standard deviation. Now, because the chi-square distribution is not symmetric, it's not going to be a matter of just, your point estimate plus or minus a margin of error. There is actually no margin of error formula here. Margin of error, adding and subtracting a margin of error only works when your distribution is symmetric. Because your distribution is not symmetric, there need to be completely separate calculations for each of the endpoints. So for variance and standard deviation, there is no margin of error formula. What we're going to do is we're going to use the critical values chi-square R and chi-square L to construct the confidence intervals for variance and standard deviation. Now, the point estimates that you're going to be using, remember, are sample standard deviation, S, or sample variance, S squared. So these are the formulas to construct the confidence intervals for variance and standard deviation. Most problems, like on your homework or on any exams, are going to ask you to do both. I would highly recommend that you start with population variance, because if you take a close look at these two formulas, the only difference between the endpoint formulas for variance and the endpoint formulas for standard deviation is that the standard deviation has a square root, because remember, standard deviation is the square root of variance. So if you do all of the hard calculations for variance first, all you have to do to find the endpoints for standard deviation are to take their square roots. So for the confidence interval for sigma squared, the population variance, the left endpoint is going to be n minus 1, those are your degrees of freedom, times s squared, which is, either your sample variance if you're given sample variance, or sample standard deviation squared if you're given sample standard deviation. Then you're going to divide that by the right critical value chi-square R. Then the right endpoint of your interval estimate for variance is going to be that degrees of freedom again, n minus 1, times either sample variance or sample standard deviation squared. And then you're going to take all of that and you're going to divide it by the left critical value, chi-square L. Then once you have your left and your right endpoints for variance, all you have to do is take the square root of each endpoint to get the endpoints for your confidence interval for population standard deviation. So here are, in words, how to construct a confidence interval for variance and standard deviation. So you're going to verify that the population follows a normal distribution. You're going to identify the sample size, and then you're going to get the degrees of freedom. Degrees of freedom is n minus 1. Then you're going to figure out your point estimate S squared. So if you're given sample standard deviation, you're going to square it to find your sample variance. If you already have your sample variance, you do not need to square it again. Then you're going to find the area to the right of chi-square R and the area to the right of chi-square L using these two formulas. Then you're going to find the critical values chi-square R and chi-square L that correspond with the given level of confidence and the degrees of freedom using the chi-square distribution table. Then you're going to plug all of that in. You're going to first find the confidence interval for variance. Then, once you have found the confidence interval for variance, you're going to take the square root of each of your endpoints to find the confidence interval for population standard deviation. So let's actually do one. So let's say that you select and weigh 30 samples of an allergy medicine. So right away, your sample size n is equal to 30. The sample standard deviation is 1.2 milligrams. So sample standard deviation, that is your variable S, so S is equal to 1.2. Assuming the weights are normally distributed, so the population's normally distributed, we're going to construct a 99% confidence interval, so C is equal to 0.99, for the population variance and the population standard deviation. All right, so right away, since our sample size is 30, we need to identify the degrees of freedom. The degrees of freedom is going to be one less than the sample size, so we have 29 degrees of freedom. Next, let's get our critical values chi-square r and chi-square l. So we're going to start with the area to the right of chi-square r. So the area to the right of chi-square r is going to be 1 minus the level of confidence, 0.99, over 2, and that will give you an area to the right of 0.005. So what you're going to do is you're going to look up in the chi-square distribution table an area to the right alpha of 0.005 with 29 degrees of freedom. So at alpha equals 0.005 with 29 degrees of freedom, that will give you a chi-square r of 52.336. Then we're going to look up chi-square L. So we're going to find the area to the right of chi-square L next. Which will be 1 plus our level of confidence, 0.99, divided by 2, gives us an area to the right of 0.995. So if you look up in the chi-square distribution table, an alpha of 0.995 with 29 degrees of freedom, you get chi-square L equals 13.121. Now that we have our two critical values, we're going to construct our confidence intervals, and we're going to start with the one for sigma squared or population variance. So for the left endpoint of your interval, it's going to be n minus 1, so 30 minus 1 is 29, times s squared. Well, s was 1.2, so we're going to take 1.2 and we're going to square it. We were given standard deviation, so we do need to square it here. Then we're going to divide it by chi-square r, which was that 52.336. And then for the right endpoint, we are going to take n minus 1, which was that 29. We're going to multiply it by s, 1.2, and since that's standard deviation, we're going to square it. Then we're going to divide it by chi-square L, which is that 13.121. Now, each of these are going to come out to really gross decimals. So when you're writing your final answer, you are going to round them. But I would highly recommend you take the square root kind of as is with all of those numbers after the decimal point, just to make sure that you are keeping your interval estimate accurate when you go to find the endpoints for standard deviation. But rounded off, we get a left endpoint of 0.80 milligrams. And a right endpoint of 3.18 milligrams. So then, all we have to do is take the square roots of each of these endpoints, and I would highly recommend you not using the rounded values, use the big giant decimals that the calculator gave you. So if you take the square root of the left-hand endpoint, rounded off, you get about 0.89. And if you take the square root of the right endpoint, rounded off, you get 1.78. So this is your confidence interval for sigma squared, and this is your confidence interval for sigma. So the interpretation is that we can estimate with 99% confidence that the population standard deviation of this allergy medicine is between 0.89 milligrams and 1.78 milligrams, and the population variance for this allergy medicine is between 0.8 milligrams and 3.18 milligrams. So I've kept a lot of the values the same, but I do want to demonstrate what happens as the level of confidence gets lower, what happens to the interval estimates. So we still have that, we're still weighing 30 samples of an allergy medicine, so n is equal to 30, which gives us a degrees of freedom value of 29. The sample standard deviation is going to be 1.2, so your s is equal to 1.2. Assuming the weights are normally distributed, this time we're going to calculate a 90% confidence interval for the population variance and population standard deviation. So because our confidence level is different, we are going to have to recalculate chi-square r and chi-square l, this time with c equals 0.90. So let's start by finding our critical values. So we've got the area to the right of chi-square r first. So the area to the right of chi-square r will be 1 minus the level of confidence, 0.9, divided by 2, gives you an area to the right alpha of 0.05. So if you look up in the chi-square table an alpha of 0.05 with 29 degrees of freedom, you get a chi-square r value of 42.557. Then we're going to do the same process to find the area to the right of chi-square r. So the area to the right of chi-square L, right, of chi-square L. All right, so the area to the right of chi-square L is going to be 1 plus the level of confidence, 0.9, divided by 2, gives you an area to the right of 0.95. So if in the chi-square table you look up an alpha of 0.95 with 29 degrees of freedom, you get a chi-square L value of 17.708. Now that we have our critical values, we are going to construct our confidence intervals for variance and standard deviation, and we are going to start with variance. So sigma squared. On the left, we're going to take n minus 1, which was 29, times our sample standard deviation, 1.2 squared. And we're going to divide it by our chi-square r, which is that 42.557. Then for the right endpoint, we're going to take n minus 1, which was that 29. We're going to multiply it by our s, 1.2 squared. And then we're going to divide it by chi-square L, which is 17.708. And then rounded off, you get your endpoints for sigma squared to be 0.981. And then for your right endpoint is going to be 2.358. Now, I would recommend going out several more decimal places when you take their square root. So go out more decimal places than I have written here when you take the square root of each endpoint to find the endpoints for standard deviation. So if you take the square root of the left endpoint for variance, you will get a left endpoint for standard deviation to be about 0.99. And if you take the square root of the right endpoint for variance, you will get the right endpoint for standard deviation, which was 1.536. So those are your two confidence intervals for variance and standard deviation. So for the interpretation, with 90% confidence, we estimate that the population standard deviation of this allergy medicine is between 0.99 milligrams and 1.536 milligrams. And the population variance for this allergy medicine is between 0.981 milligrams and 2.358 milligrams. So that is it for constructing confidence intervals for population variance and population standard deviation. And this is actually the end of Chapter 6, and this is the end of confidence intervals, and these are the confidence intervals that we're going to be doing in this class. So after this, we will start Chapter 7, which is hypothesis testing. So just make sure that you have wrapped up the Chapter 6 homework before you start the lecture series on Chapter 7. So thank you all very much for watching, and I will see you in the next video.